Okay, selection is one way to alter the default flow of control in a program. So remember that by default, statements are executed from the top of the main function to the bottom. One might want to alter this behavior. One might want to alter the flow of control for many reasons. For example, maybe your program is going to calculate an hourly worker's weekly pay. If the worker works more than 40 hours, typically they earn a little bit of extra money for any number of hours over 40 that they worked. And if they worked 40 hours or less, then it's just their normal rate. Right? So we can kind of think of this as saying, well, if the hours worked was greater than 40, well, then we're going to do one thing. We're going to calculate the pay by taking the first 40 hours times their normal pay rate. So we know for sure they worked at least 40 hours, right? Because we said if this is true, then we're going to do that. Okay, so we're going to take 40 times the pay rate and add to that hours worked minus 40. These are the additional hours over 40. So if somebody worked 50 hours, for example, 50 minus 40 is 10. There's 10 overtime hours. And we can multiply that by 1.5 times the pay rate. So this is time and a half. If we sum those two numbers together, that you get a little bit extra for those extra hours over 40 that you worked. However, if the number of hours worked was not greater than 40, right, if it's less than or equal to 40, well then the way we calculate the pay is we just take the number of hours worked times the pay rate. Okay, so we want to do one of these calculations, but not both. Okay, so we've basically come to a fork in the road where we get to this point and we check to see did the person work more than 40 hours? If so, we do one thing. If not, we do something else. Okay, but never are we going to do both things. Okay, so the way this works in code is that we, the programmer, make an assertion in code, and we let the computer determine if that assertion is true or false. If the assertion is true, one block of code is going to be executed. If it turns out to be false, then another block of code is executed. So I can show you an example here. Let's say we are going to have this little bit of code to determine what to print out based on somebody's grade. Let's say on an assignment or something. So we have an integer variable called grade. So remember, when the flow of control reaches this point, imagine a box being created in your memory called grade, and it can hold an integer value. Then we prompt the user to enter in a grade, and then we read in a value from the keyboard, and whatever number gets typed in at the keyboard is going to be placed inside the box called grade. Okay. Now, if the grade was excellent, if it was 90% or better, so if this is true, we're going to print out that you earned an A. However, if this is not true, we're going to go down here to this block and say, well, you did not earn an A. Okay, so when the flow of control reaches the line that starts with the if, we're asking the computer to look at our assertion and determine if it's true or false. If the assertion ends up being true, based on the value entered by the user, then the first block will be executed. Otherwise, the second block of code will be executed. In other words, the programmer asserted that the value inside the variable called grade is definitely greater than or equal to 90. Now, this may or may not be true. We let the computer compare the numbers to actually determine it. If the computer determines it is true, the computer will then execute the first block of code. If it is not true, if it's false, it will execute another block of code. But it will never be the case that both blocks of code get executed. Okay, so we ask the computer to evaluate these things called logical expressions. And logical expressions are assertions that the computer determines whether they are actually true or false. The result of evaluating a logical expression is always either true or false. And these are such important terms that true and false are keywords in C++. Okay, those are reserved words. Those are special words. They have meaning in our C++ programs. Okay, we can have logical expressions with Boolean variables, relational operators, or logical operators. And we're going to talk about these in great detail here. Let's start with Boolean variables. Remember in the last lecture we talked about some of the built-in types like int and float and char. Okay, there's another type called bool. And a variable of type bool can only hold one of two values, either true or false. So let me show you a snippet of code here. Okay, here's how we declare a Boolean variable. So B-O-O-L is the data type. So when the flow of control gets here, this says, go carve out room in memory for this piece of data called isTuesday, and its type is bool. That means we can only store one of two values in there, either true or false. Okay. So here I'm just hard coding a value, but let's pretend the value might come from a calendar or something like that. This assigns the value true to the variable called isTuesday. Now, if the value inside the bool is true, okay, so when the flow of control gets to this if that value is true, we're going to execute this code. We're going to go to class. However, if this is not true, we're going to jump down here to the else block and do something different. In this case, study for class. Okay, so again, basically we've come to a fork in the road where we're saying, well, is it Tuesday? If true, we're going to go to class. If it's not Tuesday, we're going to study for class. And then no matter what, we always go back to our normal sequential flow of control. So you might hear me refer to Boolean variables as flags. That's just a term we programmers use. The name bool, incidentally, comes from one of the first mathematicians to think about computer logic. The guy's name was George Boole. The only problem is that he was born, hundreds of years ago, so he didn't get to see any of his work actually used in a modern computer. And I think a lot of people thought he was just a nut. But he was really influential in, or at least he was the first one to really think about how a machine can do logic. Okay, the next type of logical expression that we have are ones that involve these things called relational operators. Okay, and these should be pretty familiar to us. We have less than or equal to, greater than or equal to. This is an interesting one. When you want to compare two things to see if they're equal, you don't use a single equal sign, you use a double equal sign. Okay, so the single equal sign, that means we're going to assign one value to another. The double equal sign means we're going to compare two values together to see if they're equal. And then lastly, this symbol is the not equal. Okay, so the computer can tell us how numbers relate to each other. Remember earlier we talked about this thing called the ALU, the arithmetic and logic unit? Well, it does the arithmetic and the logic, and in this case, logic means comparing numbers together and determining if our assertions are true or false. Okay, so this is kind of interesting. We can make these assertions, and the computer can tell us whether those assertions are true or false. So for example, we can ask the computer, is the number 10 less than the number 12? And the computer would tell us, yep, that's true. 10 is less than 12. We can ask the computer, is 1 less than or equal to 2? The computer would tell us, yep, that's true. We could ask the computer, is 20 not equal to 20? So we have to think about this one here. Is 20 not equal to 20? No, that's false, because 20 is equal to 20. Here's another kind of curious one here. Is 5 greater than or equal to 5? Well, 5 is not greater than 5, but it is equal to. So it's true that 5 is greater than or equal to 5. And then lastly, is 23 greater than 89? Well, the computer will tell us, no, that's not true. Okay, or that's false. Okay, the computer can also do this with variables, and this is what makes these programs so powerful. Let's imagine we had three integers called x, y, and z that held 10, 10, and minus 3. Okay, so we can ask the computer, is x not equal to y? And what the computer is going to do is going to be the exact same thing that I'm going to do here. I'm just going to go and look up here. Well, what's inside x right now? Looks like it's the value 10. And then I'm going to go replace y. Well, y also has the value 10. And then it's going to say, well, is 10 not equal to 10? And that, of course, is false. Okay. So whenever you refer to the name of a variable inside code, remember what happens. The computer goes and finds that box, takes the value inside that box, and uses it in the expression. Okay. So now when we ask, is z greater than or equal to y? Well, let's plug in the values for z and y. We have -3, and y is the value 10. So is -3 greater than or equal to 10? Well, no, that's false. Is y less than 100? Let's see. Is y has the value 10. Is 10 less than 100? That's true. Okay. Here we have kind of a complicated one. 4 times y divided by 8. Is that less than x minus 5? Okay, here I might just rewrite this. Okay, and plug the values in. So we have 4 times y. Y has the value 10. Divided by 8. Is that less than, let's see, x has the value 10 minus 5. Okay, so let's see. Now we could start to do the arithmetic and the comparing. Remember, the parentheses force things to happen first. So we have, we actually have a nested set of parentheses here. That means we want this arithmetic to happen first. 4 times 10 is 40. Okay. 40 divided by 8 is 5. And over here we have 10 minus 5, that's 5. So the question is 5 less than 5? And of course that's false. Okay, 5 is not less than 5, it's equal to 5. Okay, we have another kind of complicated one here. Let me replace all the values for this one. So we have -3 times z. So what's inside z? Well, it's the value -3. Okay, plus 2. Is that greater than or equal to 2 times x? And we know x holds the value 10. Minus. Now we're going to take the opposite of z. Okay, so this minus sign here is taking the negation, or asking us to reverse the sign of this value. So z is -3. If we take the opposite of that, that would be that's eventually going to be +3 times 3. Okay, so let's see. -3 times -3 is +9 plus 2. That's going to be 11. Is that greater than or equal to, let's see, 2 times 10 is 20, minus, remember, -3 is actually a +3. +3 times +3 is 9. 20 minus 9 is 11. And here the question is 11 greater than or equal to 11? And we know that's true. Okay. So the only tricky thing with the relational operators, remember, is the double equal sign. If we want to compare two things to see if they're exactly equal to each other, we're going to use the double equals. Some other notes about comparisons using relational operators. When comparing floats, remember that floats rarely hold exact values. So I think I did this example last time. 10 divided by 3 is really 3.3 repeating. Okay, so you might think if we compare 3.3333 to 10 divided by 3, you might think, well, this should be true. Okay, but most likely this will evaluate to false. Okay, why? because, again, the result of doing this arithmetic is going to be close to the real value, but not exactly, right? Because we know there's an infinite number of 3's. Right? You know, a mathematician would say, well, that's 3.3 repeating. But all of our boxes have a fixed size. It's a finite size. So we can't put an infinite number of bits inside a finite-sized box. Okay, instead, what we should do is, when we're dealing with floats, is not check for exact equality. What we can do is we can check for near exact equality. Okay. So what this does, this bit of code uses this function called fabs. Fabs is short for the floating point absolute value function. So fabs is a function that returns the absolute value of a float number. So to compare two floats, we can just subtract them, take the absolute value, and then see if the difference is really small. That's my 0.001 there. And you can use whatever threshold you'd like to consider, you know, really close, okay, or the difference being really small. When comparing characters, okay, so that's what we have to deal with when we're comparing floats. When we're comparing characters, the upper and lowercase letters have numeric values that allow them to be compared alphabetically. Okay, so if we were to ask the computer, is the character A, remember when we refer to hard-coded characters, we always put them in single quotes. Is the character A less than the character B? Okay, is lowercase a less than lowercase b? In this case, this is true. Okay, the letter A comes before the letter B. If we ask, does the letter X, is that less than, or does that come before the letter F? Here we know that's false. Okay, unfortunately, the case of a letter does matter. So the lowercase letters have numeric values from 97 to 122, and the uppercase letters have numeric values from 65 to 90. Okay, so remember from the last lecture, I said a character is really just an integer. It can hold a relatively small number. The only thing that's really kind of unique about a character is when you print out a character, instead of printing out the number, it goes and looks in this thing called the ASCII character chart, which I have a copy of right here. Okay, and what you'll see here is the uppercase letters. This is the value for the uppercase A is 65, uppercase B is 66, and so on. Uppercase Z is 90. Then we have a few characters, and then we start to see the lowercase letters starting at 97 and going all the way up to 122. Okay, so again, a character is really just a number. It's an integer. And when we print out a character, instead of printing out that number, it goes to this chart and prints out the corresponding character. So notice there's just about everything on your keyboard is in this list somewhere. Okay, and then there are some non-printable characters over here that we won't worry about right now. Okay, what this means to us is that if we compared lowercase a to uppercase a for exact equality, unfortunately the program would tell us, well, no, that's false. Okay, because this one had one numeric value and this one had another. Okay, and maybe even more confusing is if we say, is lowercase a less than uppercase b? Okay, that's also false. Why? Because when we're comparing values, it's going to compare the numeric value of the character. So lowercase a was 97, and uppercase b was 66. Is 97 less than 66? Well, no, that's not true. That's false. Okay. Okay, so you have to be careful with the case of letters when you're comparing them. Now with strings, basically the same rules apply to strings, because a string is just a collection of characters. However, when you compare strings, you're basically doing a letter-by-letter comparison. So you can ask the program, is the string Mark less than the string Mahoney? Okay, and basically what's going to happen is the computer's going to go character by character and say, well, is uppercase M less than uppercase M? Well, those are the same, so we can't say for sure that this string comes before that one. So we'd go to the next character, and we'd say, well, are the A's, is lowercase a come before lowercase a? Well, again, we don't really know. That doesn't tell us anything about the whole word yet. Then we get to the third letter, and we say, is the R less than the A? Or, I'm sorry, the H is the third letter. So is R, does that come before H? Well, no. So what we can say is that the word Mark does not come before the word Mahoney. So when you're comparing strings, think of it like looking up words in a dictionary. Okay, and the less than basically means, does this word come before another word in the dictionary? Okay, so those are our relational operators. Our last type of operators are called logical operators. And we have three logical operators. They are called and, or, and not. Okay, so it's easiest to explain these by looking at these things called truth tables. And the truth tables explain when a logical expression evaluates to true and when it evaluates to false. So it's worth committing these three tables to memory. I've put them in the slides here. Okay, let's start with and. Okay, so the logical and, unfortunately, and is not used as a keyword. Instead, we use these two characters here, the ampersand characters, to represent the and operator. Now, the logical and operator is called a binary operator. In mathematical expressions, the binary operators allow you to do arithmetic on two or more numbers. And the simple arithmetic operators are addition, subtraction, multiplication, and division. We also have these things called operands. These are the numbers that the operator applies to. Okay, so I'm going to use the same terms, operator and operands. Right? So every binary operator, of which plus is 1, has two operands. These are the things that are on either side of the operator. And these are the things that the operator is going to apply to. So when we say 1 plus 2, we're saying sum up the values 1 and 2, sum up the values of the operands. Okay, with the AND operator, both operands must be true in order for the whole expression to evaluate to true. In other words, the operators are going to be logical expressions themselves. So here's an example. We can ask, is 10 less than 20? That is a logical expression that's going to evaluate to true or false. Okay, so 10 is less than 20. And is 5 greater than or equal to 5? So that happens to also be true. Okay, so the operator is and, the operands, in this case we have two true values. And what we can do is we can go to this chart and say, well, true and true, the result of applying the and operator to two operands that are true, we get a result that's also true. Okay. If we say true and false, that gives us false. False and true is false, and false and false gives us false. So what you have to remember, the only thing you really have to remember, is that with an AND operator, AND only results in true when both operands are true. In the other three cases, when there's at least one false, the whole expression evaluates to false. Okay, so we could say true and true. We could go and look at our table and see, well, true and true gives us a result of true. Okay, so I know this one, the overall result is this is true. Now how about this one? We have, is 20 equal to 21? That's false. And is 4 less than 8? That's true. So we could go look at our table. False and true gives us a value of false. Okay. So I know the overall result of this one is false. We could also do these types of logical expressions involving variables. Okay, so let's look at the values here. Again, I'm just going to go through and replace these. So let's see, we have z is 2, x is equal to 10. Is that equal to, let's see, y is equal to 20. We have 4 times x is 10. Is that equal to z times y? 2 times 20. So 2 times 10 is 20. Is 20 equal to 20? That's true. 4 times 10 is 40. Is 40 equal to 2 times 20, which is also 40? Is 40 equal to 40? That's true. True and true. We know this overall expression evaluates to true. Okay, let's see here. Let me put a different value in for x just to show you a false value. Instead of 10, maybe we'll put in the value 100 for 10. For x, I mean. Okay, so let's do this again, and this time let's say x is equal to 100. So let's see, z times x, 2 times 100, is that equal to 20? And 4 times 100, is that equal to 2 times 20? So 2 times 100 is 200. Is that exactly equal to 20? And is 4 times 100 is 400. Is that equal to 40? So let's see, is 200 equal to 20? That's false. And is 400 equal to 40? That's also false. We could either go to our memories, or we can go look up in this chart. False and false. The result there is false. Okay. Okay, so that's the AND operator. Remember, the only time AND evaluates to true is when both operands are true. Next we have this thing called an OR operator. Okay, the OR operator is, again, we don't use the word OR. We use these two vertical bars. And if you're looking at your keyboard, this is the key just above the Enter key, but you have to hit Shift and this key to get a bar. And to do the logical OR, you need 2 bars. Okay, so let's just quickly take a look at the chart here. True or true is true. True or false is true. False or true is true. The only one that ever evaluates to false with OR is when we have both operands equal to false. So false or false is the one and only time we get a false value. Okay, so let's do this again here. Now notice we have the OR operators here. Is 10 equal to 20? That's false. Is 5 greater than 5? That's also false. False or false, I happen to know, is false. You could look up in the table, but false or false is false. Is 20 equal to 21? That was false. Is 4 less than 8? That's true. So false or true, I happen to know is true. False or true gives us a value of true. Okay, we can also use some variables here. Again, I'll just plug in some values. Z was 2, y is 5, x is equal to 10. 4 times 10, is that equal to z times y? 2 times 5. So let's see, 2 times 5 is 10. Is 10 equal to 10? That's true. 4 times 10 is 40. 2 times 5 is 10. So is 40 exactly equal to 10? That's false. True or false? Our final value there would be true. Okay, and again, I could change the value here. Why don't you kind of pause the video and put in the value 100 in for x and evaluate this expression, and I believe you will get a false value. Okay, let's move on though to our third logical operator, is called the logical not. Okay, not is not a binary operator, it's called a unary operator. It only has one operand. So not negates or takes the opposite of the operand. So if your operand is true, not true is false. If your operand is false, not false is true. Okay, so is 10 equal to 20? That's false. Okay, but then when we apply the not operator to this expression, not false, that makes this whole thing true. Is 4 less than 8? That's true. But not true makes this whole expression evaluate to false. Okay, not can be applied to any logical expression to get the opposite value. Okay, one note about these logical expressions: we have to obey the operand operator rules in the language. So for example, some people might read this expression, the one that's boxed here. They might read it as I is equal to 3 or 4. I is equal to 3 or 4. The problem is that we want I to be compared to each of the numeric values first, and then we want to perform the OR operation. So comparing for equality is a binary operation. We need two operands. So we need I to be compared with 3, and we need I to be compared with 4. Okay. What we have up here is we have an equal sign here, but we're not comparing I to both 3 and 4. If we want to do that, we must do it like this. This is the correct way of comparing. Is I equal to 3 or is I equal to 4? Okay. Let me give you another kind of similar example. A lot of times in a math book you'll see something like this. 12 is less than y, which is less than 24. That's just another way of saying that y is somewhere in the range of 13 to 23. Okay, but we can't write it like we have written in the box here. It must be written like this. Again, because of the same rules, the binary operator, the relational operators are binary. So we must say 12 is less than y and y is less than 24. Lastly, we'll talk about short circuit evaluation. That means if the computer can decide early on what the value of a logical expression is going to be, it will not perform the entire operation. Okay, so let me give you an example. Okay, here we have two variables, x and y. X is equal to 10, y is equal to 100. And here we're doing this comparison. Is x equal to 20? Well, x we know is 10. Is 10 equal to 20? That's false. Okay, so what the computer would do at this point is it's already evaluated the left-hand operand, and it goes and looks and says this is an AND operation. And if you go back to your chart, your AND chart, you'll see that anytime the left operand was false, that would be the bottom two rows here, the result was always false. Okay, so here x is not equal to 20. So we know the first operand is false. So the computer will not even bother executing the y less than 1,000. Okay, this will not even get executed because it really has no effect on the overall expression. No matter what, the whole expression is going to be false. And we know that as soon as in an AND operation, when the left-hand operand results in false. This is called a short circuit evaluation. Here's another example. X is equal to 10 or y is greater than or equal to 0. So x is 10. So is 10 equal to 10? That's true. Then the computer looks at this and says, well, that's an OR operation. If we look at the table, any expression that the left-hand operand is true is always going to result in a true value. So for exactly the same reasons, we won't even bother executing this part of it, because true or anything is going to give us a value of true. And false and anything will give us an overall value of false. Okay, so this makes sense, and the reason that we do it is it'll save the processor from doing some work. It does take a small amount of work to do this comparison, but if we know for sure what the result of the expression is going to be, there's no point in doing that extra work, right? Because whatever happens over here is going to have no effect on the overall result of the operation. Okay, so we've talked about these logical expressions in great detail. Let's go back to C++, and our assertion syntax says that we put a logical expression inside an if statement. Okay. And when the flow of control reaches the if, the computer evaluates the entire logical expression. If the expression is true, the first block of code is executed, and the second block is skipped. Okay. So if this logical expression, the flow of control gets here, if the logical expression evaluates to true, we're going to execute this entire block of code. Remember, a block of code is delineated with these curly braces. If the expression happens to be false when the flow of control gets here, we're going to skip the first block and execute the second block, okay, or what I call the else block. It will never be the case that both blocks of code are executed, because a logical expression cannot be both true and false at the same time. Okay, you should always indent inside of a block, and the editor will add these tabs for you. Just go with the flow and let the tool do its thing by tabbing in for you. It makes the code much easier to read. Let's see, a few other things. You can have an if without an else. That's perfectly fine. So here's an example where maybe we only want to recognize people that get a perfect score. So if the grade is exactly equal to 100, we'll say, hey, you received a perfect score. But we don't want to diss people just because they didn't get a perfect score. So what's going to happen here is when the flow of control gets here, only the people who got exactly 100 will see this printed out. If you got less than 100, well, you just won't. There isn't anything special to do. We don't want to, like I said, we don't want to insult people just because they didn't get 100. So if the grade is not equal to 100, this block will just be skipped, and we'll go pick up with our normal sequential flow right here. You can also nest one if inside another. Okay, so here we're saying if the grade is greater than or equal to 60, okay, that means that's a passing grade. If that's not true, though, then we know that's a failing grade. Right? Once we get inside one of these blocks, we have another if that we say, well, if the grade is greater than or equal to 90, we already know for sure it's greater than or equal to 60. Otherwise, the flow of control wouldn't have gotten here. So we know it's greater than or equal to 60, and now we're checking, is it also greater than or equal to 90? If so, we tell them they're excellent. Otherwise, we tell them, although you passed, you can still do a little better. Okay. If the grade was not passing, then the flow of control would have jumped in this block and we would have said you failed. But now we do a check to see, well, did they even attempt? Did they turn anything in? If the grade is equal to 0, we say, well, you didn't even turn anything in. If this is not true, what that means is they did turn something in, it was just really bad. So try harder next time. Okay, so really there are 4 paths through that code. Right, so we had this kind of sequential flow of control, and then we said, well, did you pass? And based on the values inside the grade, maybe you did, maybe you didn't. If they did, you'll take this path and you'll print something out. But then you check again, did you get was your grade greater than or equal to 90? And again, that's either going to be true or false. And we print something out. The way these ifs work, as soon as you're done with the if or the else block, you always go back to the normal sequential flow. Okay, the people who did not pass, right, we did a check. We printed out that they didn't pass, and then we said, was their grade exactly equal to 0, meaning they didn't turn anything in? Or did they turn something in and it was just poor work? Okay, so this is that nested if, and you can see there really are 4 paths through this code. Here's one, that's a really good grade. Here's another, this is a passing grade but not excellent. Here's a failing grade where nobody turned anything in, and here's a failing grade where they turned something in and it just was no good. So those are the 4 paths through this code. You might want to think about paths as you're writing code and when you're thinking about how to solve problems. Typically, if an if allows you to go down one of 2 paths, if you want to select from more than 2 branches, you can with this thing called an if-else-if test. Okay, so the syntax is very similar. Okay, so this bit of code is going to choose from one of 5 different paths. Okay, where again it's going to look to see it's going to compare the value inside grade to see if it's greater than or equal to 90. If so, we'll print out an A. But if that's not true, then the flow of control will go to the next if, and we'll say, well, is the grade greater than or equal to 80? And if it is, we'll print out B. If it is not, we'll go on to the next one and say, well, is the grade equal to 70? Okay, so after one logical expression is found to be true, all the others are going to be skipped. And the flow of control will pick up with the first statement outside this big if-else-if statement, which is down here, this last C out. Because these tests are done from top down, only one of them will ever get executed. In other words, the only way we will ever check to see if the grade is greater than or equal to 80 is if we already know for sure that they didn't receive a 90 or greater. Right? Because if they had received 90 or greater, they would have executed this and skipped all the other ones. So the fact that we're even comparing grade to 80 means that we know for sure this was not true. Okay? And this allows us to choose from not just one path, okay, but many. Okay? So basically we can see, well, what's the grade? Is it greater than or equal to 90? We'll do one thing. Is it greater than or equal to 80? We'll do something else, and so on. Okay, so we have all these different paths to choose from, and then no matter what, one of them is going to get selected, and then the flow of control is going to go back to our sequential flow. So this is not a great picture, but imagine a kind of a fork in the road where we have more than one fork. We do something, and then all these paths lead back to, again, our normal sequential flow. Okay, and that's selection. Selection is a very powerful thing. It's fundamental to just about every single programming language there is.